Okay, let's talk about the relationships, similarity and right triangles. Oh, I want you to look up what are CryptoKitties. They're non-fungible tokens. So look it up and see what they are. You'll become rich one day. Anyway, so the opening problem is you have a right triangle. So we're going to put a right triangle with the base on the ground. Right, and this right triangle has sides 6, 8, and 10. It's a right triangle. It's a Pythagorean triplet. And so, but the question is, what happens if, first of all, if I drop an altitude from the right angle to the base? The question is, what is the length of what is the length of that altitude? And so you can use Pythagorean triplets and equations, and so let's go through this. So let's see, I'm trying to get a relationship together. I know that, but I need these other sides. So I can say, you know what? If I let this length here be y, then this part here is 10 minus y. And so I can set up two equations. So I have, let's see, x squared plus y squared equals 6 squared. And I also have x squared plus 10 minus y squared equals 8 squared. So my intention is that I'm going to solve for x squared. So I have x squared equals 36 minus y squared. And on the right, I'm going to have x squared equals 64 minus 10 minus y squared. Since they're both equal to each other, I could technically set them equal to each other. So I have 36 minus y squared equals 64 minus, and then I'm going to expand this out, 100 minus 20y plus y squared. And then I have, let's see, 36 minus y squared equals 64 minus, well, let me just do that quickly. So 64 minus 100 is 36. 64 minus, that's plus 20y and minus y squared. I know that the y squares cancel out, and I have, this was negative 36. So I have 20y equals 72, and y equals 3.6. That gave me how the base is broken up into 3.6 and 6.4. The question is, what's this x? Well, put it back into Pythagorean theorem. And we get, what do we get? We got 3.6 squared plus x squared equals 6 squared. So x squared equals 64 minus, so 36 minus 12.96 is equal to, what is that equal to? 23.04, and it ends up being x equals 4.8. So, but what if I told you that there's a much faster way to do this, and that x over 8 is equal to 6 over 10, and then we have 10x equals 48. So this is method 1, and then method 2 is simply we can set up these ratios. X over 8 is equal to 6 over 10, so x equals 4.8. And then with my y, I can say that 4.8 over 8 is equal to y over 6. And that means 8y equals 28.8, and therefore y equals 3.6. So the question is, do I do method 1 or do I do method 2? And method 2 takes into account of similar triangles. So the question is, how are we going to figure this out? This is much faster because I don't want to do all this, solve quadratics. But if I can do this, so there must be a faster way. Well, it's very simple. First of all, we need, you can see here we have ratios. And the question is, how do we know those sides are in proportion? Well, let's investigate. So what we're going to, once again, we're going to look at a right triangle. We take a right triangle, right? And we have, it's a right triangle, and what we're going to do is drop an altitude again. Now, the first thing is we see 3 triangles here. I'm sorry, let me move the computer over. Here we go. We have 3 triangles there. We have a left triangle, we have a right triangle, and we have a big triangle. Now, the first question is, how can I prove that all three of these triangles are similar? Well, what did you think about that? Okay, we're back. So, how I would teach if I was in front of you is I would say, we're going to insert something called dummy variables. Because I don't know what those angles are. I don't know what the measurement of those angles are. So let's call the first one alpha. Alpha, and then the other one we'll call beta. So down here, this acute angle is alpha, and its complement is beta because these are all right triangles. Well, we know that alpha plus beta equals 90 degrees because the acute angles of a right triangle. Well, look up here. This is a right angle up there. So if this part is beta, this other angle here, its complement is alpha. Same idea here in the right on the right. If an angle is alpha, its complement is beta. And what we've done is we now discovered that these three triangles, the left triangle, the right triangle, and the big triangle, are all similar to each other. This is kind of cool. Now, you may ask, okay, so what are we going to do? So the technique I'm going to talk to you. So first, the way I used to teach it was, first I would tell you to put the sides in. So let's see, 6, 8, 10, and x. And we're looking for x. And the idea is we're looking for some type of connection. Well, I see a lot of hypotenuses, right? I also see that x is opposite alpha in the left triangle. I notice that x is opposite beta in the right triangle. And I notice that 8 is opposite alpha in the big, right? And I know that 6 is opposite beta in the big. Let's take a visual. Let's pull these triangles apart. So I'm going to ask you to pull the triangles apart. So let's do 3 triangles. 1, 2, 3. Let's call the first one the one on the left, the second one the one on the right, and the third one is the big triangle. Next, I'm going to ask you to do one variable at a time. Well, and we'll see if we can pick it up. So let's try to fit this in. We can clearly see the hypotenuse, which is between alpha and beta, on the left is 6. I can clearly see the hypotenuse for the right. It's also between angles alpha and beta. It's 8 for the right. And we see the big triangle has a hypotenuse of 10. Next, what's the relationship in x? Well, on the triangle on the left, x is opposite alpha. Whoops, I forgot to include my alphas and my betas. So you can put out, let's see, alpha, beta, alpha, beta, alpha, beta. Okay, sorry about that. Well, let's see. In the triangle on the right, x is opposite alpha. Therefore, x is opposite alpha. In the triangle on the right, x is opposite beta. Opposite beta. And then, what about this triangle down here? Well, we're lucky because we have all the sides. We see that 6 in the big triangle is opposite beta, and 8 in the big triangle is opposite alpha. Well, you might say, oh, you know what? You say, wait a minute, now I notice something. You could compare. You could say, oh, you know what, Mr. Adler? If I compare the left triangle versus the big triangle, I can make a proportion. 6 is to 10 as x is to 8. And you get x equals 4.8. We actually could make another. How about we compare the right versus the big? You could say x is to 6 as 8 is to 10. Same idea here. And that's the idea. So this is how we're going to proceed forward. Look for draw your triangle. Draw 3 triangles. Your right, left, your right, your big. Put in your alphas, betas, and then find the corresponding sides with opposite the angles and see if you can match something up. Well, we found x quickly. Let's see if we can find the other side. How about y? So you know what? I'm going to use this in blue. I'm going to put this in blue so you can see it. How about, so I want to find this side right here. Actually, once we find that y, we can easily find the other part. So we're almost done. Let's see, what are we missing? Now, you could, if you wanted to, use Pythagorean theorem, but my claim is that you can always use similar triangles in this case. So let's take a look at y. So let's see, in the left is opposite beta, and I think that's it. Well, we're good, because we're good here. So we're good. Let's try to find y. Let's see. Let's compare, for y, let's compare the left versus the right. So let's see. I have y over 4.8 is equal to, let's compare the hypotenuses. 6 over 8, nice. 8y equals 6 times 4.8. If I divide both sides by 8, I know I have y equals 6 times 0.6, y equals 3.6, and then by subtraction I have the other side if I want it. And that's it. And that's the idea. Now, let's try another one. So, let's try one that's a classic example. So, let's get our right triangle down. We're going to, it's a right triangle, we're going to drop in altitude. And let's just start with something basic. The hypotenuse is broken up into 4 and 9, and we want to find the altitude. Now, this is old school. There's a really quick relationship between the parts of the base and the height. So let's break it up into our triangles. Left, right, alpha, beta, alpha, beta. Let's see. So I have my left, I have my right, I have my big, alpha, beta, alpha, beta, alpha, beta. Let's see. 4 is opposite beta in the left. X is opposite alpha in the left. X is opposite beta in the right. 9 is opposite alpha in the left. And I have nothing for, well, actually I have my hypotenuse here, but I don't have, these are my unknowns. We can find them a little bit later, but right now I'm interested. This is kind of interesting because you look at this, you say, you know what? You look at this, you can quickly say, you know what, let me do left versus right, and I say 4 over x is equal to x over 9. You see that x squared equals 36. Actually, I'm going to leave it 4 times 9, and x is equal to the square root of 4 times 9. This actually is known as the geometric mean. Now, you know about the arithmetic mean. You add two things together and divide by 2. You can do the same thing between two numbers, multiply them, and then take the square root. And so this is 6, and that's kind of interesting. They asked us on the SAT, like, quick little questions, like, so, yeah. So if an altitude breaks up the base, it's the geometric mean of the parts of the base. It's kind of cool. Let's go on. Can we find the other parts? So we know this is 6. You can quickly use Pythagorean theorem. Once again, my claim is that you can use similar triangles to find the other parts. Let's pick another part. How about the hypotenuse of the left triangle? That's y. Now, I call it the hypotenuse of the triangle on the left, sorry, but it's also opposite beta, right? And so right now you have another relationship. Immediately you say, Mr. Adler, let me compare left versus big. And you say, Mr. Adler, 4 goes to y as y goes to 13. And so we have y squared equals 13 times 4. I'm going to leave this undone because I have to take the square root. Take the square root of both sides. Y equals 2 radical 13. Well, we have one more side to get through. Let's do it in orange. Well, let's take a look at the z over here. Well, where does the z fit in? The z is the hypotenuse of the right, but it's also opposite. It's opposite the alpha in the big triangle. And once again, you might say, Mr. Adler, let me compare the right versus the big. So we're going to say 9 over z is equal to z over 13. Z squared equals 13 times 9. Take the square root of both sides. Z is equal to 3 radical 13. And that's what you do. Once again, identify the 3 different triangles. They obviously might be, in different directions and stuff. But the idea is, given any 2 parts, this is kind of cool. And this is only specific to a right triangle whose altitude is drawn. My claim, and we can do it right now, is that given any 2 parts, once again, if you have a right triangle and you drop an altitude from the right triangle, you can find all the other parts. You can find all the other parts. So, did I throw it away? I keep throwing it away. What's my claim? Here's an example. It might get a little tedious, but you know what? I once again with right triangle. I see this part is 5, and this part is 11. Can we find all the other sides of these triangles only given that information? Well, the answer is yeah, it's kind of cool. Set up your triangles. Let's see, alpha, beta, alpha, beta. We have right, we have left, and we have big. Let's see, left, right, big. Let's see what we can fit in here. Well, let's fill in the variables. How about we start at x, y, and z, all right? Let's see. Well, let me put my alpha betas in. Alpha beta, alpha beta, alpha beta. Let's see. Well, 5 is on the left, and it's opposite beta. Z is the hypotenuse, and y is opposite alpha. So that's a lot of variables. I'm not really sure. Let's see. What's going on with the triangle on the right? Well, opposite alpha is x, opposite beta is y, and the hypotenuse is 11. Anything else? Anything else? Let's take a look at the big triangle. Well, opposite beta is z, opposite alpha is 11. What's the hypotenuse? 5 plus 11. Well, immediately this pops out. It should pop out to you that, you know what? If I compare this to this, and I compare this to this, I only have one variable. It's brought together, and I can start solving these equations. Let's put an equation together. Let's see. So we have 11. We're going to compare the right versus the big. 11 over 5 plus x is equal to x over 11. So we have x squared plus 5x equals 121. It's not the nicest number, but the point I'm making is that if you have any 2 parts, you can figure out how to back into the other parts. Obviously, if you have, first of all, if you have the basis broken up, you can find the altitude and then use Pythagorean theorem to find the other 2 sides. Or if you have a side, and so if you have a side and a triangle, if you have 2 sides of one triangle, you can find the third side, back into the base, and find the hypotenuse. And then what we just showed is that in this weird example where you have one part of one triangle and another part of another triangle, you can still figure out how to back into all the other parts. And that's basically it. So good luck. It's fun. I like this. It's very, very interesting. this idea. So once again, instead of just doing Pythagoras theorem over and over, you now have a faster way. And this is really great for math composition problems. You're looking for relations. We're not saying these triangles are congruent, but the second we know they're similar, we can start setting up all these ratios. Nice.